So for everyone who is surprised not to see Jairo, so Jairo is busy today, so I'm standing in as part of the organizing committee of the SPICE and SPIN+X seminar series. All the credit, by the way, to Jairo for setting this up. I think I'm doing this now for the third or fourth time out of, I don't know how many dozens he has done. All right, so it is 3 p.m. according to my watch. So welcome everyone to the online SPICE-SPIN+X seminar series, which is organized by the Spintronics Interdisciplinary Center, which is run by Jairo together with Libor and Angela in Mainz, and also with Karin Everschusitte in Duisburg-Essen. And it's together with the Collaborative Research Center SPIN+X, Spin Its Collective Environment, which is organized by Martin Eschlimann and Burkhard Hillebrands in Kaiserslautern, as well as myself in Mainz. As probably most of you already know, the talks are webinars, which means you will not be able to talk during the presentation. But if you have a question, please use the chat. And then afterwards in the Q&A session, what I will do is I'll upgrade you as panelist, and then you can join the panel and also ask your question in person. However, you're also welcome to just put your questions into the chat/Q&A. We always do it at 3 p.m. on Wednesdays, and for the next couple of talks, today the 10th of April, so we don't have a one for the next week, but then there is the nanomagnetism in 3D workshop where there's no SPIN+X SPICE seminar, and then the quantum matter conference where there's no seminar, and then the hybrid correlated states and dynamics in quantum materials where also I will go, which is also organized by SPICE. And the quantum matter for quantum technologies. So this means, without further ado, we have a great speaker today, Claire Donnelly. So let me just very briefly introduce her. So she's a Lise Meitner Group leader at the Max Planck Institute for Chemical Physics of Solids in Dresden. And a very quick rundown on her career. So she did a PhD in physics in Zurich, and then was a postdoc at Cambridge before coming to Germany. And she's one of the pioneers of three-dimensional magnetic structures in terms of characterization, in particular the magnetic 3D spin structure, which was always a rather important challenge and recently got tackled by some of her pioneering work. And she has a number of honors and awards, such as the Young Scientist Award from EMMA, the Early Career Award, the ERC Starting Grant. And as I very briefly mentioned, she's also the second time she's going to talk here. So we are looking forward on an update on her activities. And with that, I invite Claire to share her screen and give us some of her new insights.
Perfect. So thank you very much, Matthias, for the very nice introduction. And again, thank you for the chance to speak again for the second time here. It's really a pleasure and an honor to be able to have the chance to, well, yeah, give you an update, but also to share, let's say, some of our more recent results with the community. So today what I'm going to be speaking about is, again, let's say last time I spoke about 3D, I'm going to be speaking about 3D magnetic systems again today. But more specifically, what I'm going to be focusing on today is the question of topological textures in 3D magnetic systems and how we aim to, first of all, map, but secondly, control them using three-dimensional geometries. But before I get into that, what I'd like to first of all start with is the most important part of the talk, which is, of course, a massive thank you and acknowledgement to the people who I am lucky enough to work with. So specifically, I'd like to say, first of all, a big shout out to my group in Dresden. I've started there a couple of years ago already, and we have a lot of fun, but we also do a lot of nice work together. I'd also like to say a big thank you to my collaborators from different large-scale facilities as well as different universities across mainly Europe. We do a lot of large-scale facility work with our X-ray imaging, and as a result, we have the pleasure to work with many really great people without whom the work would not be possible. And lastly, of course, a big thank you as well to the funding agencies who also make this possible. We get to do what we love doing. So I mentioned that the main two topics of the of my presentation today are going to be focused, first of all, on the idea of three-dimensional magnetic systems, and then secondly, looking into a little bit more detail at topological textures within these systems. And I'd first of all, therefore, I'd like to start with a motivation as to, in case you're not already convinced, why we are interested in going to three-dimensional magnetic systems. And just for a background, I think, let's say, many of us here today are, let's say, very familiar with the world of magnetism. We know that over the last number of decades, there's been a huge amount of work done that has predominantly taken place in 2 dimensions. So this is for a number of reasons. One, there's a huge amount of interesting work, or interesting physics and possible applications in 2D. And also they're a little bit more experimentally accessible than their 3-dimensional counterparts. And so already, let's say, there's been a number of devices. So we're all familiar with the magnetic hard drive. That's really still a very important part of data storage today. We can think about in these, let's say, more planar systems that we can tune their properties normally via the material itself, or looking at, let's say, thin film heterostructures. And already in these 2-dimensional systems, there's been a lot of work on looking at magnetic textures, or topological magnetic textures, such as these magnetic skyrmions, as you see here. So we see already, like, say, 2D magnetism has a lot to offer, but what we are very interested in is what happens when we go to the 3rd dimension. So for example, if we already look at this schematic taken from a review a few years ago, we see when we go to 3D, we have a number of different possibilities. So we can, first of all, think about introducing curvature into our system, which is another way of thinking of it. We're breaking the symmetry of our system. We can also think about introducing geometric topology into our system, and also purely thinking about the magnetization vector field in itself becoming 3-dimensional. So we have now the 3-dimensional space in which our spins can point in different orientations. Now, how does this affect these 3 points that we spoke about in the context of 2D? Well, already, let's say, if we think about, first of all, the case of data storage and devices, the most well-known 3-dimensional device, and possibly one of the things that kick-started people's interest in 3D nanomagnetism, is the racetrack memory that coincidentally was the topic of the same seminar, I think, a couple of weeks ago by Stuart Parkin. So the idea here is that by simply going from a planar surface to a 3-dimensional architecture, one can really achieve much higher density in terms of your data storage. Now, of course, not only the density in which benefits when you go to 3D, there's also possibilities to go to more interconnected networks. And we know, let's say, now that this interconnectivity can be incredibly important when it comes to the, let's say, for example, non-traditional computing architectures, which are, of course, also a lot of interest at the moment. Now, as well as these devices, so interconnectivity and density, we can also think about these properties. And as well as looking at, let's say, the material itself and the different thin film heterostructures, we can also play with the geometry in 3D. For example, introducing this curvature, this breaking of symmetry with curvature or torsion. And this allows us actually to introduce curvature-induced effects, such as exchange-driven curvature-induced DMI or anisotropy into our system. Now, because this is then geometric, it gives the opportunity to tailor our energy landscape within different parts of our system, and therefore explore both the physics and also potential applications. Now, lastly, as well as, let's say, our energy landscape and our fundamental interactions, we can also think about these magnetic textures. And this specifically is where we want to think about topologies. When we go to 3 dimensions and we simply go to a 3-dimensional space, new topologies become possible. And in particular, let's say we're very familiar with the magnetic skyrmion, which is defined on a 2-dimensional plane. We then, when we go to 3D, have the possibility to look at magnetic Hopfion textures, which are really truly 3-dimensional topological defects that can also exist in 3-dimensional space. So hopefully with this slide, you get a little bit of a feeling for why we're interested in going to 3 dimensions. And what I now want to look at a little bit more closely is this question of topology and topological textures, especially as a function of dimension and in particular in 3D. So when we think about topology across dimensions, let's first of all think or remind ourselves about what we mean by topology in magnetism. Well, typically topology is generally associated with the idea of smooth deformation. So we are all very overly familiar with this idea of the coffee cup and the donut, where you can smoothly deform one into another, meaning that they are topologically equivalent, but that the cup and the donut are therefore not topologically equivalent to the so-called pretzel donut, which we find in Germany, which again has more than one hole, so it cannot be smoothly deformed. The same idea of the smooth deformation happens in magnetization vector fields, where you treat the magnetization as a unit vector, and you can smoothly deform topological objects of the same topology into one another. Now, what this means is if you have topologically non-trivial objects, they cannot be smoothly deformed into a uniform magnetic state, and therefore they have the potential to have associated topological stability, so to speak, which means basically there's an energy barrier associated with their transformation into or their disappearance into a uniform state. Now, this question of topology in the magnetization very much depends on the dimensionality, first of all, of your spins, and secondly, of your space. And we can think a little bit about the different dimensionalities that we have available to us. So first of all, if we think about the simple option of two-dimensional spins in 2D, we can therefore define a winding number, so to speak, which essentially characterizes vortices and anti-vortices, which are two-dimensional spins arranged in a two-dimensional plane. Now, these are relatively kind of our simple magnetic textures. We can then go up a dimension, staying in two-dimensional space, but increasing the dimensionality of our spin orientation. We can look at three-dimensional spins in 2D, where we now are looking at what's known as the skyrmion number, where you can, by integrating over a surface, you can actually find these topologically non-trivial textures, such as skyrmions, or indeed you can have these hedgehog textures that are defined on a three-dimensional closed sphere in 3D space. Lastly, when we take then from 3D spins in 2D to 3D spins in 3D, we then get something which is known as the magnetic Hopfion, and which is then defined by this Hopf index, this topological invariant, the Hopf index. Now for this, what we really need to emphasize here is that for Hopfions to exist, we really need the combination of a three-dimensional spin texture and our three-dimensional space. And these in principle can form these kind of soliton-like textures in our materials. So we've got now, if we think about these 3D magnetic configurations, I would say different possibilities to really look at three-dimensional topological configurations. And I just want to touch very quickly on these last two and give you a bit of an overview as where we stand in our field. So if we start off with skyrmions, for example, these are very well studied configurations. There's been a huge amount of work over the last decade or more, and they are sort of often observed or typically found in chiral systems. So they're associated with chirality. And there have also been already a number of different devices proposed, for example, the skyrmion racetrack memory. Now, when we think about, let's say, taking these from a two-dimensional plane up to 3D, where this starts to become quite interesting is that you can actually have topological transformations in 3D. So these skyrmions that exist in a plane can actually then form skyrmion tubes. And within the thickness of a system, you can actually have transformations of the topology, where you see one skyrmion transforms into two, associated with the presence of a Bloch point singularity. So you have now the possibility for networks of these complicated skyrmion tube configurations. And of course, let's say you can have more complicated configurations such as skyrmion braiding and so on. So let's think then, we can see already with the skyrmion textures that we can already have some quite interesting magnetic configurations. Let's think a little bit now about these Hopfion textures. And so these were actually the topic of I think the talk last week by Nikolai Kiselev. He will have, let's say, talked a lot about this. So for those of you who want a more in-depth discussion, you're more than welcome to go and have a look at this talk. But essentially, to give a quick overview of where we stand in the field, let's say as of the last 5 years or so, Hopfions have become, or magnetic Hopfions have become really a topic of real interest. So it started off with a growing number of theoretical works where we predicted both that these textures could be metastable, how potentially their static and dynamic configurations look like. But it was much more recently that we actually had the first experimental observations of such textures, both in these thin film heterostructures, as you see at the top, but also observed in with electron microscopy. So albeit with two-dimensional imaging, they were able to observe Hopfion rings and fractional Hopfion states in chiral magnets. So you can see already now we've got a number of different possibilities and already first few observations of these complex 3D textures. And so what we really need in order to go to the next stage, in order to really understand and potentially control these systems, is first of all to think about how we can observe these in 3D. So when we think about experimentally how we want to investigate these systems, what my group and my colleagues are very much been working on over the last few years is kind of building a toolkit for investigating 3D magnetic configurations and magnetic systems experimentally. So this toolkit involves, let's say, three main areas. We have, first of all, the question of how to visualize or how to image these three-dimensional magnetic configurations. Secondly, how we can fabricate three-dimensional geometries in order to control their properties. And lastly, of course, it's not an experiment, but more of a theoretical point of view, how we can actually understand and potentially analyze the configurations that we see. So I'm going to first of all start in this talk by introducing what visualization techniques we currently have, so what we've been able to develop over the last few years, before I then start to present some of our more recent work on these topics. So to give you a little bit of an overview as to what we have available to us now at this point in time with three-dimensional magnetic imaging, essentially for 3D imaging of magnetic configurations, we use a tomographic technique. So the idea is that you can measure two-dimensional images in transmission of your configuration. You then measure multiple sets of these projections for many different orientations of your sample with respect to your probe. And then you need reconstruction algorithms, which are developed, well, we've developed and other groups have also developed, in order to reconstruct a three-dimensional vector field. Now, there's a number of different probes that you can use in order to visualize these three-dimensional magnetic systems. There's, of course, the electrons B that look at the magnetic induction of your sample. Neutrons, which work on a much larger length scale, so you can look at very, very large samples up to centimeters in size, but with a little bit lower spatial resolution on the order of tens or hundreds of micrometers. And then you've also got the X-rays, with which we can probe directly our magnetization of our system. Now, in my work, what we mainly focus on is the case of X-rays, because I think we like to think that they have a number of certain advantages. So we have the possibility to be element specific. We can actually target, let's say, for example, the spin and the orbital moments of our configurations. And we can most importantly, perhaps, tune our X-ray energy to be able to look at larger systems, but with very high resolution. What I mean by that is systems up to micrometers in size, but with nanoscale resolution of our magnetic configuration. So to give a very first intro or let's say demo, I will very, very quickly present what we initially published as the first demonstration of magnetic tomography quite a few years ago already by now. And this is where we looked at a ferromagnetic pillar about 5 micrometers in diameter with X-ray magnetic tomography with hard X-rays. Now we make use of X-ray magnetic circular dichroism as our contrast mechanism. You can already see in these two-dimensional projections that in the lower half where we take the difference between circular left and circular right, we have bright and dark regions, which correspond basically to the magnetization pointing towards or away from the screen. So we measure typically as part of one of these data sets about 1,000 of these, or in this case, we measured about 1,000 of these projections around 2 different tomographic rotation axes. And with that, we are able to get oh, my video is not working, but this should show you a video of a 3-dimensional configuration where we can really gain access to the internal magnetic configuration of our system. Now, what we can do is take a little bit of a look as to what's happening inside this configuration. And in particular, what we see if we take a horizontal slice is that we have a number of these vortices and anti-vortices that form kind of this circulating or saddle-like structure. And these are, again, 2-dimensional essentially defined as two-dimensional spins in a two-dimensional configuration. But what we can see actually when we really take into account the three-dimensional volume of our configuration is that we have indeed these regions where the topology abruptly changes, and we see these Bloch point singularities, so Bloch points and anti-Bloch points that are effectively points at which the magnetization vanishes and associated with abrupt changes in the topology of our configuration. So these Bloch points had been seen or had been predicted, I think in the 1960s already by Feldkiller, but it wasn't until we had this technique that we were able to image them directly in real space. So we have now static imaging, but we can go further than that. We can also go on to looking into the fourth dimension where we can image three-dimensional magnetization dynamics. And for this, we make use of a slightly different technique. Rather than tomography, it's laminography. The same principle holds. It's a three-dimensional magnetic imaging technique, which we can also use for static imaging. Now here, what we do is we combine this with 3D imaging with a pump probe, taking advantage of the time structure of the synchrotron, which allows us to image with about sub 50 nanometers, on the order of 20 nanometer spatial resolution, and about between 50 and 100 picoseconds temporal resolution. And in this way, what we've been able to see is the dynamics in 3D of topological textures. So what you're seeing here is a vortex core gyrating from side to side of a particular white reference point, showing that we can map or we can track the dynamics of topological textures in a buried system. But we can also perform Fourier analysis and map out essentially where we have coherent rotation of the magnetization. So, i.e., we show the possibility to be able to look at the spin waves in magnetic configurations. So going one step further, what we had first demonstrated this was with hard X-rays. And at this first point in time, we were actually limited to about 500 megahertz, so to the 500 megahertz rate of the synchrotron. But by combining it with a different technique, which is soft X-ray time-resolved scanning transmission X-ray microscopy, which essentially uses a point diode, so a much faster detector, you can actually then start to look at resonant dynamics in 3D. So by tuning the excitation frequency of your system and also the frequency at which you can record your dynamics. Now for this, we looked at, with Simone Finizio from PSI, a kind of nice demonstration sample, which was a sample in which we have a Landau pattern. And you can see then we were able to image the dynamics of this system. First of all, at 300 megahertz, we're able to look at the dynamics of the vortex core. At 900 megahertz, looking at the dynamics of these domain walls instead. So what this really shows is now we have the tools necessary in order to be able to look at resonant dynamics of the magnetization in 3D. And I'd very much encourage anyone who thinks that such a technique could be of use for you or your samples, you're more than welcome to get in touch with me or, of course, Simone, and talk about potentially some beam time at the synchrotron for you. Now, just to give you an example of how you can potentially use such a technique, so this resonant dynamic imaging in 3D, we've recently had the pleasure to work with Davide Girardi, Edoardo Abasetti, and Daniele Petti from Milan, where we looked at resolving the three-dimensional spin waves in a synthetic antiferromagnet. And in particular, what we looked at was what we looked at was a Landau pattern again, where the domain walls in the vortex core in the Landau pattern leads to the emission of spin waves in the synthetic antiferromagnetic system. And actually, by looking in 3D about what's going on, well, we could already look at the localization of these spin waves within the bulk of the system, as well as actually look at or observe the three-dimensional interference pattern of the spin waves propagating at in different directions at where they meet. So already, so this was a nice work. It was, I think, accepted last week or the week before in Nature Communications. It's a nice demo of the fact that not only can we use these techniques for kind of proof of principle experiments, but also to look at real systems and real scientific questions. So with that, that's my kind of first overview of the techniques that we have available to image three-dimensional magnetic systems. And what I want to then go on to now, having given you this first introduction, is to talk a little bit more about more recent results within our group. In particular, I'm going to take these two aspects from my title. First of all, looking at mapping certain three-dimensional topological textures, and secondly, the question of how we can control them. So how we can use these three-dimensional geometries in order to control their behavior and ideally look towards some devices in the future. Okay, but let's start off with this mapping. And continuing along the same idea of, let's say, harnessing the techniques that I've just presented to you, we're still looking at these three-dimensional magnetic textures within these bulk-like systems. And in particular, we were going to start off with these topological textures in bulk-like systems. I then want to think along the lines of some method development that we've been able to develop over the last year or so. In particular, taking advantage of coherent imaging techniques in order to extend the capabilities of these 3D imaging techniques, and also taking the same principle of imaging with dichroic signals from circular dichroism, where we probe ferromagnets, to linear dichroism, where we can probe orientations within our sample. So, but let's start off with some three-dimensional topological textures in these bulk-like systems. And the key point here, and this is again probably the video that's not going to play, one of the main challenges that we have in these three-dimensional data sets that we get with tomography is actually the question of big data, so to speak. So we have millions upon millions of pixels, each with 3 components of the magnetization. And one of the challenges is how do we actually identify the relevant objects and determine their topology. So one direction in which we've been going over the last few years is actually developing and implementing new types of analysis of our magnetic configurations that we achieve, that we experimentally measure. And this is essentially by calculating the so-called magnetic vorticity vector. So those of you who are familiar with the skyrmion number, which is shown in this equation here, essentially what we do is we take what's inside the integral of the skyrmion number, and this gives us a vector field that encodes the topology of our configuration. Now, when we plot this, simply we can plot regions of high vorticity in our sample. We can already see that we then have a network, a three-dimensional network of magnetic textures. These are the cores of vortices and anti-vortices. But we can also go one step further, and we can look at the divergence of this vorticity vector, where this allows us to identify regions where the topology changes abruptly. And when we do this, we suddenly have access or the possibility to really image our three-dimensional distribution of these Bloch point singularities, where these red and blue points essentially correspond to Bloch point and anti-Bloch points within our system. Now with this, let's say, first access to this three-dimensional distribution of Bloch points, it really opens up the possibility to not only track them efficiently within these 3D data sets, but also to look into how they may interact with each other across these three-dimensional spaces. Now, as well as using this vorticity vector in order to, let's say, map these configurations, what we can also do is we can use it to understand particular configurations that we observe. And there are 2 textures that I want to introduce to you now. First of all, we want to look at these loops that we observed occurring in the magnetization that consist of vortices and anti-vortices, cores of vortices and anti-vortices within the bulk of our system. Now, when we plot the vorticity vector in these loops, we see actually that the vorticity vector circulates around this loop, meaning that we essentially have magnetic vortex rings. Now, these vortex rings were first predicted by Nigel Cooper back in 1990s, where he essentially, I guess, these are the first prediction of these kind of Hopfion-like textures, where potentially, if they are topologically non-trivial, then they would be similar to these Hopfion configurations. But what is particularly interesting about these vortex rings is that the vorticity that is defined by Nigel in this work is directly analogous to the hydrodynamic vorticity that we associate with these hydrodynamic vortex rings, such as bubble rings or smoke rings. And this, of course, then has very nice implications for the dynamics of these textures and their behavior if we think about trying to propagate or control them in the future. But before we go on to that, what we were particularly interested in on the topic of topology was understanding why these textures were actually stable in our system, and the question of had we observed such a topologically non-trivial vortex ring. So in order to determine this, the nice thing about having the 3D data is that we can directly perform a second type of analysis, which is essentially the direct calculation of so-called pre-images. So these are isosurfaces that correspond to a certain direction of the magnetization. So you see here this work, this image taken from the work of Paul Sutcliffe on Hopfions. The blue isosurface corresponds to one orientation of the magnetization, the red to another. And the fact that these isosurfaces form loops and interlink means that you have a non-zero Hopf index, and therefore you have a Hopfion. So what we could do with our data was do the same thing for our vortex rings. Unfortunately, in this case, we were able to determine that the links, these pre-images do not link, and therefore we do not have a Hopfion. But it does show that if we were to have such a non-trivial texture, so a real Hopfion texture, with such a technique, we are able to really determine that it is a Hopfion in 3 dimensions. Now, as well as these topologically trivial vortex rings, we also saw vortex rings that contain pairs of Bloch point singularities within their loop. And when we plot these pre-images, we actually see something that now looks quite familiar if we are looking at different topological textures in different types of systems. In particular, what we can do is we can identify this as a magnetic toron. Now, this toron texture, the reason why I say it looks familiar is that if we have a look at work from the field of liquid crystals, for example, they have also observed toron-like textures in liquid crystals. And what's quite interesting is that they observe them alongside these Hopfion textures. So it gives us some hope that, let's say, for systems that host toron should also be able to host these Hopfion configurations. In addition, micromagnetic simulations have predicted that, again, that these torons and Hopfions can be stabilized, let's say, in the same system, and also that they can transform dynamically one into the other as well. So, okay, we've seen already in this data set that we don't see any Hopfions, but we can go back and, let's say, remind ourselves of where we are actually in the field coming back to today. And of course, we have this very nice work from the end of last year where Hopfion rings were observed in these chiral materials, giving with this 2-dimensional electron imaging. So it really gives the hope that, well, it gives a demonstration that Hopfions can exist, which is absolutely fantastic, but also it gives us a hope and a bit of a direction of where to look if we want to image these configurations in 3 dimensions. But one of the challenges, of course, is, well, finding the right material. We have an indication now of what this material could be, but the question is also the geometry of our system. It needs to be, of course, 3-dimensional, but how 3-dimensional does the system have to be in order to stabilize these Hopfion textures? Now, I'm talking about this now very much in the context of our magnetic imaging. So what I want to pose the question is, do we actually have our capabilities ready to be able to image such 3-dimensional textures experimentally in 3D? And essentially what we can boil it down to, I would say, if we think about what we need in order to image Hopfions in 3D, we need the capability to target different types of materials, and we need material flexibility. We need to be able to give it space, so give enough space for the Hopfion to form. And of course, we also need our high spatial resolution imaging. And so if we think about these 3 aspects and we think about what we have available at the moment for 3D imaging, we kind of actually see that we don't have a technique that combines all 3. So on the one hand, we have higher energy X-ray imaging, such as I've shown you so far, where we can really look at these micrometer worth materials, size materials, but we're actually limited in terms of which materials we can actually look at. So you can get very nice imaging with rare earth materials because of the type of dichroism that we get at the rare earth edges. But when we go to transition metals, we have almost no contrast whatsoever, significantly weaker contrast, which makes the imaging in 3D particularly challenging. And you can see this demonstration on the top right here. This is the same sample. It's an iron gadolinium multilayer. When we look at the gadolinium edge and the iron edge with roughly the same statistics, we can see that we can clearly see what's going on in the gadolinium, but the iron is much, much more challenging to resolve experimentally. Now, on the other hand, we have with soft X-rays and with electron microscopy, we have no problem in terms of the magnetic contrast. We have access to different absorption edges, so we can get much stronger magnetic contrast. And we also have very high spatial resolution. However, the challenge here is that we are typically limited to thinner samples because of the fact that the penetration depth of these probes is not quite as strong. And so the question we wanted to pose ourselves was, can we combine all three? So can we combine this flexibility in space, material with high spatial resolution in order to essentially provide the technique we need in order to image three-dimensional textures within arbitrary sample configurations? And it turns out for that, we now go to the second point, which is coherent imaging. So coherent X-ray imaging, and in particular, the topic of X-ray tychography. Now, let's see, in order to understand the context of this coherent X-ray imaging and why it provides the advantage that we need, we can take a little bit of a step back and we can consider magnetic microscopy in general. So we, of course, have the advantage of X-rays compared to, for example, optical light, that they are highly penetrating. So you have the possibility to look through thick samples. But you have, and also a disadvantage that we have this small refractive index, means that it's hard to create the optics to really take advantage of the small wavelength of the X-rays. What this means is that you rely on diffractive optics, which requires very high resolution nanopatterning. And essentially, traditionally, a lot of X-ray microscopy hasn't taken advantage of this. So for example, if we think at scanning transmission X-ray microscopy, they take advantage of these diffractive optics in order to nanofocus the beam and raster scan this across a sample, giving us our high spatial resolution images. But now the question is, what happens if we want to go beyond the limit of the lenses and actually go towards this wavelength limited resolution for X-rays, which now takes us down towards, or even potentially in the future below, the 1 nanometer level. And this now, well, the technique or the ability, the way that we can do this actually is to go towards this coherent imaging, such as tychography. The idea now here is that we take a coherent beam, we measure these coherent diffraction patterns rather than nanofocusing our beam. We take a large beam where we measure coherent diffraction patterns in the far field for overlapping illuminations, and we apply reconstruction algorithms to recover high spatial resolution and highly quantitative images of our sample. And now immediately you see in this nice comparison, tychography on the right and SPICE-SPIN on the left, that suddenly, because we're not limited by the lenses, and you have really quantitative data, you can get beautifully high contrast and high spatial resolution imaging of your systems. And indeed, up until I think very much last year, where there was some holography work that overtook it, one of the world record demonstrations of high resolution imaging for magnetic imaging with X-rays was held by this tychography technique. So you can see in this magnetotactic bacteria that you can achieve really high spatial resolution imaging with XMCD of magnetic configurations. So you see we have these coherent imaging techniques, and so far what we know is that they give us really high spatial resolution. But it turns out that for our problem that we have, which is the case of, let's say, low penetration depth of soft X-rays, the tychography also gives us another advantage. And in order to understand that, we need to understand where the problem lies initially. So what we have done actually here is we've performed some spectral tychography, so we gain access to our complex spectrum. And we can see already the issue that occurs here is that our XMCD in the absorption case, so our absorption XMCD, very much lies at the point where we have maximum absorption of our sample. Now, what this means is that typically then XMCD imaging is going to be limited to thin samples, which are highly absorbed, or which are not so as highly absorbing as thick samples. But what we can do is if we look at the complex, so the phase part of our XMCD signal, we actually now see that we have this blue signal, which is the phase, that is no longer limited to the regions of high absorption, but actually extends into the pre-edge of our sample, of our absorption edge. Now, because it extends into the pre-edge, we have the possibility to image this same sample at an X-ray energy where we have much lower absorption, and that offers the potential to go to thicker systems simply by us retaining our high contrast XMCD. So we went on to try this, and indeed we were able to look at a variety of different iron gadolinium multilayers grown by Alish Rabic from PSI, and you can see as we go thicker with the film, so yellow is already 100 nanometers, we go to blue, which is almost 2 micrometers in thickness. On resonance, we basically get 0 transmission. But even at 2 micrometers, we get a little bit of transmission in the pre-edge where we expect this phase signal to be. Now, what we can then do is we can, as we go up in thickness, compare our amplitude and phase XMCD. So essentially amplitude being our absorption contrast. And we can see that whilst the amplitude signal, pretty much we lose it pretty quickly as we go to thick systems, with our phase signal, we can actually even image with relatively high quality up to almost 2 micrometers worth of material. What this means is that we have now the possibility to take this high contrast imaging of almost any material. We're no longer limited just to rare earths, and then let's say image the 2-dimensional projections, which are the basic ingredient for 3D magnetic imaging. So this, hopefully, the next step is going to be 3D. Don't unfortunately have the images to show you now, but this is something that I hope I'll be able to show you in the next few years. Okay, and lastly, let's say on the topic of the method development, I want to mention now an additional direction that we have been going, which is the idea of taking advantage of linear dichroism. Now, what this idea encapsulates is the idea essentially of going beyond ferromagnetism. So far with circular dichroism, what we can probe are vector fields of our ferromagnetic or ferrimagnetic textures with the X-ray magnetic circular dichroism. But when we think about probing linear dichroism, we suddenly now think about, instead of vector fields, orientation fields. And now there's a few different aspects that we can start to think about. We have, of course, antiferromagnets, where our orientation field would be our nail vector. We have, of course, crystal orientations, and we can actually apply this same principle to a wide variety of different material systems. But the question is, okay, we want to now think about using this linear dichroism to image orientation fields in 3D. Can we actually do this? So where we started off, we didn't yet, can't yet show you any antiferromagnetic 3D imaging, but what I can show you today is some linear dichroic tomography of the orientation of crystallite orientations within a 3D system. And in particular, what we can have a look at are these catalysts and this work was really led by Andreas Apsaros at the PSI, who's doing his PhD there. We have catalyst of vanadium oxide, and similar to the idea of circular dichroism, when we perform linear dichroism, we gain access to the in-plane components of our orientation field. And what this means, if we perform, again, phase X-ray linear dichroism imaging, so we are again using tychography, we can have now a projection of the components of either the horizontal or the vertical orientation. Now, what we do essentially is we combine this concept again with this multi-tilt axis tomography in order to essentially measure enough data to be able to reconstruct our 3-dimensional orientation field. And so, okay, I won't go into the details of how we did this. If you're interested, I'd be more than happy to talk about it. But essentially what we can see with this data set is we already get a number of different sets of information. We first of all, purely from the non-resonant imaging, we get the electron density, which allows us to map the internal structure of our sample. And we can see here that it's formed of different, what look like grains or pieces, that are randomly orientated within this about 5-6 micrometer diameter pillar. But what we can then do is we can have a look at what we get from our orientation tomogram. And here now you see immediately that the color is indicating the orientation in the plane, that we can see a three-dimensional map of our crystalline orientation within our system. And not only can we see, for example, that we have a relatively complicated orientation map, but while some, let's say, regions appear to be single domain, we would say in magnetism language, we also have other regions that look like they would in principle be one piece, and they actually are composed of multiple crystal orientations. And we can actually use this orientation tomogram to segment our data sets, so to identify crystal grains within our system, which of course would be very useful for a wide variety of different materials. But what is particularly interesting here is that not just can we, let's say, segment the grains, we can have a look at what kind of defects we see within this crystallographic orientation. So first of all, as I mentioned before, we can have a look at the grains themselves. So we're able to identify and map single crystal grains, as you can see here, where we have pretty much a single orientation of our crystal orientation within the isolated piece. But we're also able to identify regions where we have grain boundaries. So we can identify actually within our data set twin, twist and tilt grain boundaries. We have a twin grain boundary here. And we can see even though in the electron density we were not able to really identify any loss or decrease in the electron density at this boundary, we can nicely identify it from the crystal orientation. Now, as on top of that, we don't only just see these grain boundaries, but we're interested in topology. And so we were also looking at the different types of defects that we can see within our system. And indeed, actually within our, let's say, more merged, denser areas, we're able to identify different topological defects within our crystal orientation. So we have this comet-like and trefoil defects, and we can actually follow how they can create and annihilate. So they merge if we follow them through the three-dimensional space. This, let's say, was very exciting to see now that we have this new capability. But of course, as you can imagine, this is not where it ends. I can't show you any more today, but we're very excited to look at not only taking on this crystallographic information and potentially combining it with operando measurements. So this could be interesting for all kinds of different materials, but of course, trying to apply this to different types of orientations within different systems. So the next goal on the list is, of course, antiferromagnetic domains and imagining what we could do with three-dimensional antiferromagnetic configurations. Okay, so with that, I've mainly been talking so far about our mapping capabilities and everything, but in the last 10-15 minutes of the talk, I want to touch on the second topic of my presentation, in which I want to talk about the control of these topological objects. Now, in order to control them, what I want to talk, or what I would like to really focus on, is this idea that we can geometrically tune the energy landscape of our system by going towards 3D geometries. And in particular, the idea is, or the idea that we want to focus on, is this idea of introducing curvature and torsion, which typically we can see if we even take a simple exchange, let's say Hamiltonian, and convert this or transform this into a curved coordinate system, you get exchange-driven anisotropy and chirality terms popping out. So you can really, let's say, start to, by introducing curvature, introducing symmetry breaking, now tune the interactions of your system. Now, there's been already quite a lot of work done to this extent. If those of you who are interested in an overview of this, I would very much recommend Dennis Sheka's review paper here. But we've already, in the last few years, started to, let's say, explore this direction with experimentally. So we, for example, by patterning chiral geometries, we can actually saw that we were able to stabilize chiral helical states in a simple ferromagnet rather than a heliomagnet. We can also, now this was work by Vladimir Kravchuk and colleagues, where they showed by introducing this curvature onto a Thin film, you can locally stabilize skyrmion-like textures. And of course, there's also the question of actually changing, so locally within the sample, changing your geometry. So this can actually lead not only to locally defining or local changes in the energy landscape, but also so-called domain wall automotion, where you have the spontaneous propagation of defects such as domain walls. Now, if we want to then say, we've got the possibility of tuning our magnetic properties with curvature and torsion and artificial chirality. Now, before we go into our results, we also need a method, and this I would like to first of all present to you, essentially a 3D printing technique for magnetic nanostructures. So the technique that we make use of is focused electron beam induced deposition. This was developed by, the 3D printing with FEBID was developed by Amalio Fernandez Pacheco, who's now in the TU Wien. And the idea here is that we have a scanning electron microscope chamber. We can introduce a precursor gas into this chamber. And with the focused electron beam, we can locally deposit our material. Now, depending on the gas that you introduce, you can deposit different types of material. So, for example, the standard one is platinum. We can also deposit tungsten, which actually turns out to be superconducting. And of course, we also have cobalt, a cobalt precursor that allows us to directly deposit magnetic nanostructures. And the typical idea is that you can go to a CAD software and define your three-dimensional geometry, feed it into Amalio's program, and in the end, go to your microscope and really pattern a three-dimensional geometry of your choosing. Just to give you an idea of what you can really do with this, we've said that we are interested in curved surfaces, but then also in topological objects. Luca Skoric, who was the PhD student on this project, went away and did some very nice demonstrations of the types of materials or types of systems that we can actually realize. So you can see here on the top, we've got really a three-dimensional object that has different types of curvature. And on the bottom, really a Mobius strip shown in there, realized in 3D, all below 1 micrometer in size. So we really now have this new capability to be able to realize three-dimensional magnetic nanostructures. So with that new capability, there's two quick techniques or two quick projects that I want to present to you. And the first one takes account of geometric chirality, so really patterning chiral objects such as helices. And the second one, we look at the question of introducing curvature to have effective chirality in our system. But let's start off with these chiral structures, so these double helix structures. So the idea here is that we have a double helix where we don't have any overlap between the two helices, but we have them really spatially separated. Now, what this means is in our system, we have the combination of exchange, magnetostatics, exchange and curvature and torsion, but then also strong magnetoscatic coupling between the two individual helices. We can use our FEBID technique to realize this system. As we can see here, we have our cobalt nano double helix. And we, of course, go to the synchrotron in order to image the magnetic configuration. So when we have a look at the as-grown state, we can see that one helix is black and the other helix is white. And that essentially means that they're pointing in the opposite directions. So we have the anti-parallel state, which turns out to be the ground state of the system that grows naturally. But what we can do actually is if we apply a strong field perpendicular to the long axis, we can actually trap regular arrays of domain walls in our systems due to the geometry. And now we have this regular array of domain walls. The question that we were asking ourselves was, what effect does this three-dimensional geometry have on the domain walls, our double helix structure? And in order to determine this, what we, of course, do is we perform our 3D magnetic imaging. So we perform our soft X-ray magnetic laminography. And with that, we're able to really resolve the magnetic configuration within these double helices. And then what's particularly interesting here is if we consider the direction of the magnetic field that was applied, we can see that within the domains, we have the magnetization generally pointing parallel to the magnetic field, but we have within the domain walls, the magnetization pointing anti-parallel. And so what essentially we have is we have these domain walls reversing due to the strong magnetostatic interaction between the domain walls. So between these transverse domain walls. Now, because they are tightly coupled by magnetostatics, what is very interesting is that they actually form a bound state that is relatively robust to small-ish fields, so on the order of 20 to 30 millitesla. So we have these, not only do we have this regular array of domain walls, but we have them relatively robust, almost similar to the idea of a synthetic antiferromagnet in magnetic thin films. But okay, we have, let's say, the magnetic state and the magnetization. Where this gets actually even more interesting is if we consider the magnetostatic interaction itself and the influence that the 3D geometry has on the magnetic induction, so the stray field surrounding these domain wall pairs. And in particular, if we look at the magnetic induction in the plane perpendicular to these domain walls, we can actually, and we plot the magnetic induction, including both the stray field and the magnetization, we see something quite, again, familiar when we think about our topological mindset. Within the magnetization, we have effectively what's going on is the chiral structure is forming these so-called effective vortices in the magnetization or in the magnetic induction. But at the points where we have the domain walls, we actually see something that looks more like this saddle-like structure. And indeed, what we are able to see is that because of these chiral double helix structures, we are able to actually stabilize these anti-vortices in the magnetic induction on the nanoscale. So very nice from an interesting point of view. You can kind of draw analogies between cross-tie walls in even like permalloy strips and now the magnetic induction pattern that we see in the surroundings of this three-dimensional geometry. But it also is quite interesting if we think about potential applications of this technique. So we now have potentially the opportunity to be able to use three-dimensional geometries in order to pattern different textures into the magnetic induction, which of course could be of use or potentially of use for applications such as particle trapping or optics, if we were to dream a little bit. So yeah, we can see the take-home message of this work is that not only is the 3D geometry interesting for the magnetization, but also for the field itself. Okay, and then I think I have a few more minutes left. And with that, I'd like to tell you about one last project, which is our work on these undulating structures that came on the archive this morning, actually. So I'm very happy that we managed to get this on before the talk. So the idea here is that we want to explore using this idea of curvature and symmetry breaking to tailor the energy landscape and explore the physics of singularities, so these block point singularities within magnetic systems. Now, just to give a bit of a step back and a bit of an overview again, and I'd like to mention that this work was really led by Sandra Louise Gomez, who's a Marie Curie Fellow in my group and is now moving at the end of this month to start her own group in Alba synchrotron. The idea that we are exploring here is this idea of symmetry breaking. So we're very used to breaking symmetry in the unit cell and introducing the Jelisin-Skimmer-Vega interaction, or if we have, let's say, asymmetric stacks. But what we can now see is if we introduce curvature or torsion, we can get effectively the same thing. And there's already been a number of works where people explore using this aspect or this phenomena to change the energy landscape of chiral objects. So for example, people look at the pinning of chiral transverse domain walls, or look at the curvature-induced stabilization of skyrmions, as I mentioned a few slides back. But what has not been done yet is what has not been addressed yet is this question of achiral objects. And what we're particularly talking about here are these point defects, which correspond to these block point singularities in the magnetization. So these topological defects, basically. These are, because they're a point defect, they're intrinsically achiral. And what we wanted to explore was whether we can actually use this curvature and curvature-induced symmetry breaking to change or tailor the landscape of such singularities. Now, what we can actually use or make use of in this project is the fact that, luckily for us, when we go to three-dimensional magnetic systems and indeed cylindrical magnetic nanowires, we automatically have a system that hosts these block points in the form of these block point domain Bloch point containing domain walls. And so what we essentially do is we can take one of these nanowires which hosts Bloch point domain walls, and we can introduce curvature. Now, how do we introduce our curvature? Well, we again use the same technique, which is this focused electron beam induced deposition, this 3D printing technique. And essentially what Sandra has done is she's patterned with VEBID a nanowire which has a varying curvature, which is very nicely defined by the CAD file that she initially designs, where we have lower curvature on the left-hand side and higher curvature on the right-hand side. We, of course, want to image the magnetic configuration. And for this, again, we go to the synchrotron, which is our measurement technique of choice. But this time, rather than doing 3D imaging, what we perform is XMCD shadow PEM. So essentially, the idea is that our nanostructure is kind of hanging above the surface. It's suspended above the surface. And if we come in with the X-rays at a shallow angle, we can image the shadow of the X-rays on the surface of our substrate. And in this way, you can see here that the bright part here is actually the structure, but the dark part here is the absorption of our nanostructure. When we take XMCD, we can actually directly image the magnetic configuration in this way. So the first question, of course, was, can we inject a domain wall? And the answer was yes. We have here our magnetic nanostructure. Just to mention, the black-white contrast actually corresponds to a single domain state because we are coming with our X-ray from the side, so it's pointing parallel and anti-parallel, but this is purely the projection. But when we apply a magnetic field in situ along the long axis of the nanowire, you can see here at this red arrow that we have a sharp, abrupt change in the contrast. Now, this change in the contrast indicates that we have a magnetic domain wall. And we can determine what type of domain wall we have by imaging at different orientations. So we do this essentially, and we see contrast as a function of angle that is consistent with the presence of these Bloch point singularities. What is particularly nice, though, is as we continue to increase the magnetic field, we can propagate our domain wall along the structure. And we see that two things, first of all. We see that the domain wall is always present in the straight part of the structure, and that as we increase the domain wall, as we increase the magnetic field, we go from straight part, as you can see here, to straight part to straight part, overcoming one by one the energy barriers that are represented by the regions of, or the curved regions in our system. So essentially what we can do when we extract the pinning fields, we can determine the extent of the energy barriers that are represented by these curved regions. And we can actually see that quite nicely that by introducing regions of high curvature, so low radius of curvature, we can introduce relatively high energy barriers, which corresponds to pinning fields of the order of 20, 30 millitesla. Essentially what this shows is that in this way, we can actually tailor the energy landscape of the Bloch points with this curvature-induced chirality, and this opens the new possibility to explore the physics of these systems further. Okay, so with that, I am pretty much done. I've shown you today, let's see, I've given you a bit of an introduction into our work on 3D imaging, but I've also tried to show you quite a bit of new results that we've had recently. So extending really our capabilities in terms of our methodology to, first of all, thick samples, which we hope will host interesting configurations in the future, to going towards linear dichroism, which opens the possibility to go towards different types of material systems. And then, of course, using the 3D geometries in order to tune and control these properties. I think there's a lot to look forward to in the next few years. Of course, looking at the behavior of these textures in 3D. Of course, we're joining the race or the hunt for hopfions. And we're also thinking about extending these same principles beyond magnetism to different types of quantum materials. So thank you very much. And I'd be happy to answer questions.